All right. So hello, everyone. I'm just going to briefly talk to you today about some of the results of aligning some of the uh, unknown lipids in our laboratory data sets. Sorry, just give me a moment. The Unknown Lipids project, this is a screenshot from Charles Evans' lecture from yesterday regarding the project. So, I mean, a brief summary is that we had some common specimens such as lipids, brain, heart, muscle, and others. And, you know, 4 labs analyzed these specimens, the lipid extracts, using both a common method and an in-house method. And our goal was really to find some of the commonalities and to see where our gaps in our identifications from lab to lab. Much of the talk yesterday was on the common method, but my research is mostly with regard to the in-house method, the individualized standard operating protocols. So there's been much talk in this consortium meeting about the idea of standardization of LCMS protocols. And, you know, it would certainly make the task of alignment between our data sets from different labs much simpler. But the reality is that for the current and immediate future, we have very different standard operating protocols. We have different instrumentation. I'm listing just several of these from the individual institutions. Of course, there's gradients and other things that I don't have complete information of, but they're very different. And the of course, goal is to align the data between the laboratories and to compare notes on our identified and unidentified lipid features. So I designed a tool called Metabcombiner that handles this non-identically acquired data set alignment. I published a paper on it in 2021, but I'm planning to publish an expansion of it for hopefully soon. But we can take a pair of data sets and align them by mapping the retention times from one data set to the other and using the master charge, retention time, predicted versus observed, and relative abundance to compare features. And then once we have the results of one alignment, we can add more data sets. So it operates in a pairwise manner, but we can align more than 2 data sets. But one data set is specifically chosen to be the central or the primary data set, and I chose data set 1 for this. And so we can align, we can project the retention times using Metabcombiner, and I'm just showing some of the images of the fits from both positive and negative mode for all the 3 other institutions right here. And so just showing the alignment results for all features, both known and unknown. And I mean, I was pretty taken aback at just how small, it was much smaller than expected, the level of intersection among all tables. So just showing across all 4 data sets and then between subsets of the 3 that were not among the 4 and some that were individualized between 1 lab and so forth. And then looking at the named features. So this, I mean, these are just showing the same name from one lab to the other, not accounting for the stereochemistry. Some labs were more specific than others. But among the positive mode results, we had 55, which the breakdown for the most important classes are shown below. So 16 PCs all the way up to 4 triglycerides, and then 16 in the negative mode. So, I mean, I'm still investigating just what could be the causes of this lower than expected intersection. These are just some of the factors that may be, I mean, liquid chromatography can affect how separated the isomers are and how many isomers get detected in conjunction with the extraction and the pre-processing software. And then, of course, Metabcombiner specific parameters that affect how well we align features and how stringent our criteria are for accepting an alignment or rejecting one. So this has just been my basic overview of the work aligning these tables, and I'd just like to acknowledge the same people from yesterday, the different labs that were involved, and of course the funding and the sources of samples. And with that, I will open the floor to questions.
All right.